ever stop and think about what's really happening when you boil a pot of water? I mean, it seems so simple, right? But the physics behind that bubbling pot is actually what powers so much of our world. Today, we're going to follow that journey, step by step, to see how substances like water change state and how we can predict their every move. Okay, let's get into it. So here's the game plan. We'll kick things off with a definition of a pure substance that might actually surprise you. Then we'll trace water's epic transformation from a liquid into steam. After that, we'll see how to actually map this journey on a diagram, learn how to read the engineer's secret weapon, the property tables, and finally, we'll look at a super useful shortcut called the ideal gas law. All right, first up, we gotta get our terms straight. And this first one, it might just challenge what you remember from high school chemistry class. So let me just ask you this. What could a single, simple compound like H2O possibly have in common with the air all around us? A mix of nitrogen, oxygen, argon, a whole bunch of stuff. Well, in thermodynamics, they actually share a really important label. Believe it or not, they are both considered pure substances. And this is a huge takeaway. In our world, a pure substance is anything with a fixed, uniform chemical makeup all the way through. So, a mix of oil and water? Nope, not a pure substance because they separate. But a mix of gases like air is considered a pure substance because it's all blended together perfectly. Okay, now that we've got that definition locked in, let's get to the main event. We're going to watch a sample of water inside this piston cylinder gadget as we slowly add heat. We're going to see exactly how it transforms, one state at a time. And here we are at state 1. We're at room temperature, standard atmospheric pressure, and our water is what we call a compressed liquid. All that fancy term means is that it's just stable liquid water. It's not even close to boiling yet. Now let's turn up the heat. The temperature climbs and climbs until, bam, it hits the boiling point, 100 degrees Celsius at this pressure. Right at this instant, it has a new name, saturated liquid. Think of it like this. It's holding every last bit of heat it possibly can without turning into vapor. One more tiny bit of energy, and the show begins. So as we keep adding heat, something really weird happens. The temperature stops. It just stays locked at 100 degrees. Instead of getting hotter, that energy now goes into turning the water into steam. This phase is called a saturated liquid vapor mixture. You've got liquid water and water vapor hanging out together in perfect balance. We keep pumping in heat at that same temperature until the very last drop of liquid finally gives up and becomes vapor. That's state 4. We call this a saturated vapor. It's the mirror image of a saturated liquid. It's a gas that is right on the edge of turning back into a liquid. Okay, so all the water is vapor now. If we add even more heat, the temperature finally starts to climb again. Let's say we take it all the way up to 300 degrees Celsius. What we have now is a superheated vapor. It is way past the point of condensing, and it just acts like a normal gas. So that was a pretty cool journey through 5 different states. But how do scientists and engineers see this whole process in a single picture? Well, they use special maps. I mean, how do we take that physical process we just saw, the heating, the bubbling, the expanding, and turn it into something we can actually predict and calculate with? That's where property diagrams come in. Check this out. This is a temperature versus specific volume diagram, a TV diagram. Now, specific volume sounds complicated, but it's not. It's just the opposite of density. It's how much room a kilogram of the stuff takes up. So this map beautifully shows what happens to that space as the temperature changes. The path we just followed is traced right on this chart. And see that big dome in the middle? That is the most important part. Inside that dome, you've got that liquid-vapor mix. To the left of it, you have your compressed liquid, and way out to the right is your superheated vapor. Now here's what's really cool. If you change the pressure, you change the map. It's a fundamental rule. You crank up the pressure and the boiling temperature goes up too. This is exactly how a pressure cooker works. By running at about 3 times normal atmospheric pressure, it makes the water boil at 134 Celsius instead of 100. And that's why it cooks your food way, way faster. Now, diagrams like that are awesome for getting the big picture. But engineers, they need the exact numbers. For that, they put away the map and pull out a super detailed guidebook. These things are thermodynamic tables, or for water, we just call them steam tables. They are just lists of incredibly precise data for any temperature and pressure you can think of. They've got specific volume, sure, but also things like internal energy and enthalpy, which are really just fancy ways of measuring the total energy packed inside the substance. For an engineer, these tables are basically the Bible. I know, they look like a wall of numbers, but using them is actually pretty simple. First, you figure out what state your substance is in. Is it a compressed liquid, a saturated mix, a superheated vapor? Then, you find the right table and look up the one thing you already know, like the temperature. And finally, you just read across the row to get all the other properties you need. Easy. So the tables are precise, they're the gold standard. But sometimes, you don't need all that detail, especially when you're dealing with gases in certain situations. For those times, there's a really slick shortcut. And here it is, the famous ideal gas law, PV equals RT. It's just a beautifully simple relationship between pressure, volume, and temperature. But here's the catch. You have to remember it's an approximation. It works like a charm for gases when they're at really high temperatures and low pressures. Basically, when the molecules are really far apart and not interacting much. So the whole game is knowing when you can get away with using this shortcut. An ideal gas is a perfect imaginary model. A real gas, like the super high pressure steam in a power plant or the refrigerant in your air conditioner, doesn't always play by those simple rules, especially when it's getting close to turning back into a liquid. If you use the ideal gas law then, you're going to get the wrong answer. So how do we deal with that? We use something called the compressibility factor Z. Just think of Z as a reality check number. It's a correction factor that tells you exactly how much your real gas is straying from that perfect ideal model. If Z equals 1, great, your gas is behaving perfectly and the shortcut is accurate. But if Z is, say, 0.I5, that means the simple equation is off by 15%. The further Z gets from 1, the more your gas is misbehaving, and the more you need this correction to get it right. So what's the big takeaway here? We started this just by watching water boil, and we ended up with this incredible toolkit for predicting how matter behaves. These aren't just things you learn in a classroom. The diagrams that map the journey, the tables that give us the hard data, and the equations that give us a shortcut. These are the literal tools engineers use to build our world, from massive power plants right down to your kitchen pressure cooker. You know, this journey from liquid to steam is happening all around us, all the time. It's making our lights turn on. It's keeping our food from spoiling. It really makes you stop and wonder, what other invisible journeys like this are happening right under our noses, powering our world in ways we never even see?